pleasure to be here again, giving a talk in the follow-up workshop. And my talk will be kind of a follow-up to the talk that Stephen gave on Monday. And most of the motivation, I hope you somehow still remember, even though there were many talks in between. But I'll briefly recall it. Stop. But basically the goal is to understand various identities between multiple polylogarithms well enough so that one can get at the applications that everyone wants to get at. So the volumes of hyperbolic manifolds. So understand multiple polylogarithms and hopefully compute regulators using classical polylogarithms. Volumes hyperbolic manifolds and special values zeta functions. In terms of Lika. So the goal is kind of to use the complicated algebra of multiple polylogarithms to get at information about the classical ones. And so just to make sure everyone still remembers the definition, I'll write the series down. So it's the sum over the cone. And I'll follow the notation of Stephen, except my indices are completely different. So he used A's and now I'm using N. But it's not super important. And so I'll take the point of view of Stephen. So really when I'm writing Lie with indices, you should think about some kind of either motivic or some framed mixed Hodge theoretic object in the background, because otherwise you have to treat these as multivalued analytic functions. And most of the nice properties only happen when you get rid of the non-trivial monodromy. So, but kind of there are, okay, in principle you can think of it naively, and most of the things I'll talk about today actually apply to the naive point of view as well. And somehow actually, so then the highbrow way of working with multiple polylogarithms actually doesn't work with multiple polylogarithms as series. It works with iterated integrals. And somehow what I will talk about today it's more important to actually think of it as a series. And surprisingly, you can prove some strong results in that basis. So either motivic or you have some Hodge theoretic, and unfortunately there's no time at all to go into any details. But these are kind of some framed objects in good categories. The problem is motivic thing is only known to be, it only has a definition when arguments are in some number fields, and the Hodge theoretic is arguments are in C. Then if you want to work with functions, you have to do variations. But I'll take a shortcut. I'll just ignore all of the finer details, and I'll just write Lie and hope that it's clear enough. Okay, so the goal is, and the important point is that if you take the algebra, you take a collection of all of these objects together, they form a Hopf algebra. Yes? Is there a question already? No. So if you take all of these objects together, take a vector space, they form a Hopf algebra if you mod out by I at least. And so it has some kind of canonically defined coproduct. And Goncharov conjecture, Goncharov's depth conjecture is some kind of relation between naive depths and kind of coproduct depth. which Stephen explained in his talk. So I will only kind of treat this as a black box, and I will state some corollaries of that, and then I will try to prove them without using Goncharov's conjecture. So, and Stephen's talk was kind of going in one direction, so you were increasing weight, and you were trying to understand what is the maximal depth possible of objects that you have. So you could take, okay, so just in case you forgot the notation, so weight and depth are these depths, so it's a number of variables of summation here, and n is the sum of N1 up to Nd is the weight. So you could either fix n and then try to understand what is maximal depth needed, or, well, so this is what Stephen's talk is. And in general, this is a really complicated thing. So we know very little about this direction, even though we know what needs to be proven. We just don't have the necessary identities. In the other direction, you can kind of do it completely differently. So even if you take functions of depth d, as the weight goes up, you get a lot of these potential objects. So we pick d. And you have a bunch of functions now, all of them in t variables, and so what are the relations? In high t, or mainly. And so it's kind of a different game. So I want to start with a few examples maybe. So for d equals 2, you get, so Stephen already mentioned all of these things. So you have, in principle, 3 functions of depth 2 and, let's say, weight 4. And I mean, it's kind of easy to go between these two. So there is a simple identity which is reminiscent of the I mean, you prove it by using double shuffle relations. It's a little bit harder to get d to 2 related to the other two functions. But this can be done, and in fact it was done by Stephen in his thesis, and a few other cases. But I mean, it kind of quickly grows out of hand, so if you start looking at depth 4 functions, for example, you take weight 25, you get a huge mess. And if you count, if you believe me, you get exactly 2024 potential functions. And so the question is, like, why do we need so many, and what can we say about it on the basis of Goncharov? And in fact, so yes,
how many you need?
Well, that would be spoiling. I'll tell you in a moment. But so this is something that we kind of realized almost by accident when we were doing something like Goncharov conjecture. So it doesn't directly predict anything, but you can derive from it a guess, and the guess is, so okay, it's actually a theorem. Sorry? '22, I guess, although the paper will appear this year. So we proved that if you assume Goncharov's conjecture, well, Goncharov conjecture, I mean, he has a lot more conjecture, we just need to assume the statement that Stephen gave in his talk. So it actually implies that of all of these 2024 functions, you just need one, and in fact it happens in all cases. So, and you only need one specific function, so the one which has all of the indices 1 except the best So this should suffice. And no. So the problem is, as with most things, so what Stephen was talking about, you can easily, if you assume Goncharov's conjecture, it directly tells you that there are all sorts of depth reduction that hold. The problem is to prove this seems like a very difficult task.
So it suffices for what?
So, okay, so let me expand. So it means that any of these functions can be expressed in terms of this function by some algebraic, it's a linear combination of this function with some algebraic arguments in the original.
The modular products are actually.
Okay, I mean, you can make it more, so modular products is always the basic assumption. You can kind of tell which kind of products are better than the others.
Okay, but so this statement is modular products at least.
Yeah, but it can be made more precise. So in a sense, this is the only thing you need, modular lower depths and products. But for the products, you can apply the same statement. So in principle, you have a collection of functions labeled by depths and weight, which generate all of them.
So suffices to generate.
Sorry?
Suffices, I still don't understand, suffices for what?
Yeah,
Each of these functions is a linear combination of these functions with rational arguments.
all, me, and
Right. Algebraic.
Algebraic.
yes. So, yeah. And the proof is kind of, okay, I mean, you just have to use Goncharov's conjecture, but it doesn't tell you anything about how to do this expression.
So do you fix both n and d?
Yeah, you fix n and
this is
d.
enough.
Yeah, if I fix n, you fix d. Yeah, okay. Fix d and n. And then there's just one function you need to study. Everything else is expressible in terms of it. And it's kind of a non-trivial thing already to do it in weight 4 and depth 2. So if you don't have any idea of where this expression may come from, it's difficult.
And the number of ones is maybe it just 2.9.
Well,
if you know how to add the numbers and get them.
okay, so this is what we conjecture, and actually what was kind of nice is we could prove this for depth 2 by a very cheap argument. So, okay, so unconditionally. And so, I want to just give one example of what this type of unconditional proof looks like. So it's a formula. It expresses the Lie-2 function. I'll just take an example in weight 4. And I'll express it in terms of Lie-1,3. But it's kind of, I mean, it's not as simple as one, but it suggests lots. I won't give the full formula because it's actually long, but only the most interesting part. So there are a few more Lie-1,3 terms, but this is the most interesting bit because it kind of goes a little bit outside of what you would expect. And so the proof is kind of, it's a two-line proof. So the identity that we use to prove this result in depth 2 is actually a power series identity that converges on some open set. And so you just use basically this definition of polylogarithms to get something non-trivial, which kind of doesn't happen that often with these Goncharov conjecture predictions, or almost never. So,
in general, are the arguments just roots of something? In a more general case, is it more general algebraic?
So that's kind of what I'm getting into. So actually, I mean, this kind of thing came as a result of some calculation, but then you can study these expressions in general, so just polylogarithms in monomials or possibly roots of monomials. And
And is that enough for depth 2?
it's that, so this is always the case in depth 2. So it's always of this type of.
Okay, so for all of
It's
the
always, so for depth 2, monomial, well, okay, nth root of monomial arguments. Work.
Kind of distribution.
It's, I mean, it reminds you of distribution, but okay, there's a lot of, so there's a lot of things which happen in depth 2, which is you try to do it in depth 3. Well, one thing I realized that I always use partial fraction identities in my computations. I never realized that actually there's a lot of structure there which one can use, and actually there are two different types of partial fraction identities. Only one of them is easily visible, and the other one is not. So it's in depth 2 they're the same, but in depth 3 they're actually quite different. And there are other kind of strange things happening. But the main thing is if you try to do it, even let's assume I just want to find some interesting expression in depth 3 and try to brute force the whole thing, throw a bunch of monomials, run a computer, linear algebra, and try to get to the answer, we couldn't kind of get anywhere as far as I remember. So we couldn't do any case that we could do by other means. So in this, and actually for some time we thought that depth 2 may be exceptional. But that was obviously wrong, because we have managed to do this in more generality, in full generality, although this is a work in progress. Up to 2024 plus optimistically, hopefully it will be in a few months, but who knows. So this is the claim, the theorem. I'll just formulate it as a positive result. So all E and 1 and D with n the weight can be expressed using D1, 1 and minus D. And so this is the main thing I want to talk about in principle. So this is the motivation, how we arrived at the whole story. But somehow the way we proved it, I think, is more interesting than the statement, perhaps. So it tells you something about spaces of polylogarithms at monomials, which no one has noticed before.
But it's the same statement, just no hypothesis.
Yeah, it's not a condition.
Yeah, sure, but otherwise it's the same.
Yeah, I just copied it. Okay, so so there's basically the idea is to try to understand what happened here. So what kind of arguments these are, and try to figure out some general structure of the space of all such objects. So what I want to do is to define. So now I'll do a little bit more implementation. So let's CD with the d-dimensional torus, and I'll use x's even though I think I use z's, but so these will be coordinates. And so I want to define some space of multiple polylogarithms evaluated at monomials in these coordinates, which I for now will define a letter for this. So this would be the good space of functions. And so the next part of the talk is actually I will explain what this space is and how to define it. But roughly, if you take any set of monomials which are multiplicatively independent, plug them in, you get a function. So that's kind of a naive thing to do, and it's not very good. I mean, it definitely will contain what I'm going to define next, but it's not like manageable object. It's not good enough. Are there any questions so far while I'm wasting my time raising the board?
Is it tractable what happens if you start doing an elliptic continuation on both sides?
Well, it is tractable, but we somehow couldn't find a good way of encoding it combinatorially. So the basic thing, so Stephen immediately, almost at the offset, he just mod it out by all products. So actually I don't want to mod out all products, but there are some functions on this torus which are kind of more degenerate than others, which are logarithms of the coordinates. So what I want to do is mod out, so it will be some space of polylogarithms of depth t, but it will be modulo the ideal generated by log xi. And in fact, this is a kind of a good operation when you look on the level of Hopf algebras, so it's a nice idea. And you also do modulo lower depth functions, because that's what we want. I mean, you have to do it, otherwise it will become even more complicated. But in principle, at the end of the day, you can, depending on your needs, you can put the stuff back in and keep track of everything almost. So I'll explain that.
So also modular lower weight and modular lower weight depths.
It's kind of, yeah, so, and there is actually, okay, so when I define the things, there's some interesting duality happening here. So yeah, things of lower depths are dual to products of logarithms with things of lower weight. And this is very non-trivial, so it's not visible at all. Kind of, if you think of these as not functions on the torus. Okay, so I want to define kind of, so this Ln of Td, it will be a span of some collection of functions, which are indexed by elements in GLD, or well, GLDQ. And it will be kind of defined in such a way. So the span modulo what I said before, modulo logs of coordinates and lower depth. And so I want to define it in such a way that actually there's an action of GLDQ on the whole thing, and it just permutes these.
So this is a linear span.
Yeah, it's a linear span. And so, and naively, so, okay, there will be also a set of indices here. So the set of indices will correspond to the indices of multiple polylogarithms, and they will be some kind of transformation on the torus. And so when A is in decimal B, Z, this phi n1 and d of A is just going to be the function Li and n1 and d of x to the power A. And I'm kind of using shorthand notation, but so A is a matrix and x to the power A is, so x is a vector of coordinates, A is a matrix, and you kind of follow the same rule of multiplication of a row vector by a matrix, but do it in exponentiation. Well, Okay, so this is what you do for SLDZ matrices, but that actually is definitely not enough. And in fact, we kind of expect that if you take all of these functions, all of the relations between them should still follow from double shuffle relations. It's not a very substantiated thing, but we couldn't find anything in general. So what you want to do is you actually want to extend it to all matrices in GLDQ. And the definition is kind of a little bit indirect. So you start with some representative of a matrix in GLD by an integer matrix. So I'll pick any m by n matrix with determinant non-zero, and I want to define this function phi of a as some kind of push forward with respect to the mapping of the torus. So phi a, it will be a, I can call this number d. So it will be some power of determinant. And I think there could be also signs, we will ignore it for the moment. And you take all kind of d torsion, all preimages of x under power of taking power of d. So it doesn't actually involve a directly, but involves the determinant. And you take d and 1 and d of light to power a. And so the thing is set up in such a way that if you have a prime is some multiple of a, because of the distribution relations for multiple polylogarithms, we get the same. So and it's also set up in such a way, so on SLDZ it's kind of clear, this is a group action. So if you act by substitution, you get an action on all these objects.
You're saying it's action on PGL?
Yes. Yes. Yeah. So yeah, I'll only use. I'll never use the kind of. Well, I'll use exactly that. Right. So basically, but that won't be like super important. So what we have is a module for GLDQ generated by certain multiple polylogarithms on tori. And we have to mod out by all of these things. So really you're working in some kind of category of framed mixed watch structures. So these are, and it's an infinite dimensional thing, but it's generated. I mean, we kind of set it up in such a way that as a GLDQ module, it's generated by just whatever the classical polylogarithms. So it's finitely generated. That's what I want to say. And so we have a kind of natural GLDQ module. So now the question is actually, can we say exactly what it is? Like, can we recognize it as a representation? And that's kind of the statement of the second theorem. But before I can do that, I have to talk about Steinberg modules. So I didn't write it down, but at this point in time, the goal is to understand this object as a GLDQ model.
Sorry, did you say it's finite dimensional?
No, it's infinite dimensional, but it's generated because of the way, as a GLDQ module, you have one generator for each choice of indices here. So it's not immediately clear with this part, but it actually this respects a group action. So it's well. I mean, unless I messed up the exponent here, but it's only one choice which makes it projectively invariant. So Steinberg module is kind of an interesting thing because it appears in many different places, and in our story it kind of appears in two ways simultaneously. Basically, so I want to say a little bit about it, but not too much. So historically, it's kind of I mean, some special representation with some representation of GLD over finite fields, which has maximal possible power of Q as its degree. And it's kind of, I think it was essentially recognized from looking at character tables and seeing this strange character which has all of its values are powers of Q. And it's the dimension is the degree of the maximal Sylow subgroup. But then there was kind of a lot of ways of describing it abstractly, and in fact, these types of representations they live in all kinds of Lie-type finite groups, and in general, for algebraic groups, you can define them. So, kind of highbrow way of defining it is you have V as a vector space over a field K. Then we define Steinberg module of the vector space V as 1 minus first reduced homology of the Higgs building, or the spherical Higgs building, the sectional precisions. So this is kind of the simplicial complex of the poset of non-trivial subspaces in V. So you can write down simplices as basically partial flags of subspaces, and you can do computations here. But there are, so if you don't want to think about topology, you can give it as a set of generators and relations. And that's actually much more, I mean, in that sense, it's much more ubiquitous. So its generators are well, some symbols. So it's basically a collection of D. So D is going to be the dimension of D. It's kind of consistent with the previous thing. So you get
N is independent, or
oh sorry, this is yeah. So you want the collection to form a basis. So you have one generator for each basis in your vector space. And you can extend this definition by saying if they're linearly dependent, you just set the generator to 0. And relations are kind of cis-circumference relations. I mean, geometrically that's what they are, but if you write it out, so there are several things that it had satisfied. So one of them is it's antisymmetric. The other thing is kind of projective thing, so it doesn't depend on the scaling of the vector. And the most important thing is the kind of circumference identity. That's why I call it this. So if you have one more vector, you have d plus 1 vectors, then you have a d plus 1 term relation. Okay. I mean, there's a simple way of going between this one description and the other. So basically for each collection of rich bases, you have a simplex in the projective space. And you pick out kind of all complete flags from that simplex. So yeah, you get n factorial flags and you sum them up alternatingly and you get a cycle.
What is V naught?
V naught? Yeah, so you basically if you have
N equals 0 to VD.
So for any collection of vectors. And so it includes degenerate cases where if any of these things is not a basis, you just put 0. And so, okay, so there's one way of thinking about it is it's so that's the only non-trivial homology group, reduced homology group of the Higgs building. Another way is you can write down generators and relations. And I mean, it's related to modular symbols. But there's actually two more ways of thinking about this.
Simple thing.
And it's a GLB module by.
It is almost
acting as
yeah. So if you act by GLV on each element,
Yeah.
the point is, as a GLV module, it kind of is the naive thing you expect. So Steinberg V is a GLV module. And if you set your field to be finite field and V to be finite dimensional vector space, you recover kind of the Steinberg representation, which is maybe more familiar. So it has lots of nice properties. For example, I mean, this description is good to relate it to other things, but you can also write down a basis for this module in a very simple way. And even though I won't use it, it's good to keep it in mind. So the basis is given by basically upper triangular matrices. So I will kind of abuse notation. So I will use the symbol square brackets to denote the Steinberg symbol of the columns of the matrix A. So for A in GLD. So this is just a shorthand. And the basis is given by square brackets of unit upper triangular matrices. And you can prove that they're linearly independent and everything reduces to these. On the other hand, you can actually, it has, in this set of generators and relations, you don't need to use all bases over Q. You can also use all Z bases for the whatever any lattice in this module, and it still gives you the same object. But that is a lot less trivial. So, so before I state kind of the main theorem, which is the relation between this polylogarithm space and Steinberg module, I just want to mention how another way in which Steinberg module kind of naturally appears. So if you do partial fraction identities, it actually is the right object to describe them, because so if you take, for example, Steinberg of Q to the n, let's pick any element, v1, vn, or we use v, and we can map it into a space of rational functions in variables t1 up to td. Well, okay. It's not here, but it's here. And the element that you map it to is basically the determinant of the matrix divided by the product of linear forms given by columns of V. And it turns out that this is actually an isomorphism. So in particular, so if you're doing partial fraction identities, this point of view helps a lot. So it tells you what the basis is, you know, what are all the generators and relations. So this is one kind of way in which this is relevant.
Why do you need Q? Is this any field? Or any
Well, I mean, the way I defined it, I defined the Steinberg module with coefficients in Q. So I want this to be also the same field. But otherwise, I think you can tweak this. Yeah, you can change this construction. So, and another way which is more pictorial. So because this is everything is defined projectively, you can think of the basis as simplices in projective space. And then kind of half of the relations are trivial. So if you take a picture in P2 of R, basically the generators are oriented simplices. So this is kind of it's the same as the Steinberg symbol. And then, so the first identity is just the orientation. The second identity is not visible here because we're already in projective space. And so the only thing that happens that's interesting is this Caesar congruence identity, and which is exactly the reason why I call it Caesar congruent. So if you add one more point, you can decompose this triangle into sum of three triangles. But it takes account of the orientations automatically, so if you do it, it actually doesn't depend on where the point is located. So it's always done correctly. And so you kind of get the sum of three triangles given the first. What kind of, well, I want to, okay, maybe I'll save it for later. It's a little bit, okay, this is a picture, it's correct, but it's misleading because actually we don't, because we mod out by all scalars, we actually don't, we cannot tell apart this picture from the projective, like the opposite triangle, which is kind of this one, which you don't want to think about it. So actually there's some identification going on. It's not just the, in the projective space it's correct, but if you think about it on a sphere, it's not exactly what's going on. So
I'm sorry, in this isomorphism you had before, the functions, you get rational functions who are also on hyperplanes, no? I mean, what do you mean it's an isomorphism?
You have to
tensor
with C. You have to tensor with C or something.
No, it's the isomorphism with the span of all such things, of all orders of linear form.
For the image.
It's isomorphic onto
It's
itself.
it's injective.
It's a hyperplane complement.
It's injective. Yeah, I was but actually, so if only the only rational functions appearing are products of one over products of linear forms, it's better to work here. It's exactly, and you can put powers here as well. So there's a way to tweak this construction to put an arbitrarily many, arbitrarily many products, linear forms in the denominator as well. So all of these things you can incorporate into Steinberg. Okay, so now I'll state the main theorem, and then with whatever time is left, I'll try to prove at least something. So there was this module which we luckily hasn't erased yet. So Ln of TD. So basically the statement is the following. There is a unique isomorphism of GLD Q modules, which I will resolve SENV, mapping this polylogarithm object, so this strange space of polylogarithms on the torus, to a tensor product of two Steinberg modules. And that's, so let me call V going to be 2 to G. But not quite yet, because there's also something having to do with weight. So, and that is accounted for by symmetric power of V. So, okay, it's not quite yet. So the statement was there is a unique, and it's not true, at least we don't know if it's true when I write it like that, but there is a unique one which sends the generators to some special elements. Sending V and 1 and D of x1, x2. So I don't only need to do it on the generators of the GLD module, so I just pick the standard one. Do the following thing. So you take what we call E1 up to E2, the basis, standard basis. Then you take ED plus ED minus 1, ED plus E1 1, tensored with ED, E minus 1, E1. And don't ask me why this notation. And, the reversal is kind of more natural, but not fundamentally so. And tensored with some polynomial, well, some element of the symmetric power, which is just a product encoding the indices here. And so on both sides are natural GLB modules, so basically extend this thing to a map. And the non-trivial, there are several actually hidden statements here, so the main thing is that this map kind of is well defined. And another thing is the image is everything on the right hand side. So both the well-definedness and the fact that it's surjective are kind of non-trivial. And that it says something non-trivial both for this object and also for the thing on the right hand side in some way. 15 minutes?
And that's the work in progress, or is that?
Yeah, everything is work in progress. But I mean, it's like manuscript in progress. The theorem is proven.
So if you use this isomorph, you could forget the Steinberg. One of them, just say you have two sets of variables, vi and wi, and you map to functions with denominators that are linear. Products of
Yeah, you could do
forms
that.
and make it completely
Yeah,
automatic.
so it's kind of nice because it tells you how to prove identities in the LMTD by just running a computer program.
Well, that's what I meant.
Indeed,
It would be more elementary, and it couldn't state that you already told us.
It's equivalent, but somehow it's, then you won't see a lot of structure. So what's kind of interesting here is that the left-hand thing is a Hopf algebra in some sense. And the right-hand thing is not obviously a Hopf algebra, but actually it turns out to be one. And the way to see it is basically by this. If you just take Goncharov's coproduct from the left and compute what it tells you on the right, it defines a Hopf algebra structure on the Steinberg.
That is some sort of natural. Later, you can see there is some natural construction.
It is indeed very natural. So this Steinberg tensor Steinberg is also a natural thing, which is a kind of a recent result by several topologists. And I'm afraid I won't be able to remember their names. So this object is the Gaussian dual module for the Steinberg. So the tensor product of two Steinbergs is somehow quadratic dual, Gaussian dual to the original thing. So it's a very natural thing to associate to Steinberg module as well. But it's kind of...
Patz and Putnam?
Yeah, it's Patz and then Wilson, but there's like two papers and I don't remember which names. So one paper actually proves that the Steinberg is Closed in some sense, and the other is identifies the dual modulus that is tensor. So I think.
So what are you going to do now to prove it?
I don't want to prove it because it's a little bit long, but I want to indicate kind of why the hell would you expect something like that. And there is actually a good reason, and it connects also to the talk by Federico Monte.
Because he had two representations and
so I kind of, the two ways of thinking about Steinberg module appear in the sense of like some conic sums, but it's a little bit of
yeah, but you see these two pieces that were representations, two different for the conical sums, you have two different integral representations.
It's more, yeah, it's more like a conical sum itself is like a pairing between two elements. And one of them is like a cone of summation, and the other is the, instead of differential form, you have this like the numerator in the Taylor expansion, denominator in the Taylor expansion. So that's kind of the idea. But, I want to...
Is there something similar here? But there's also description not with one of the linear forms, but with a cone. With a Steinberg method, some like a basis.
Yeah, okay, so basically you take your basis and send it to a cone projected by it. And then you have to mode out by flat cone, like cones which contain a line in some direction. But then it's also like an equivalent description, except, I mean, it requires the field to be ordered, so it's kind of strange. I mean, otherwise you don't get the geometric picture. Okay, so this is kind of like already been discussed, so the reason why this is true can be seen on the level of Taylor expansion. And it's, so there's a map, I mean, it's kind of strange because I only defined the map on the generators, but in principle, if I give you something which is not written as sum of polylogarithms, it's not clear. Well, so what I want to say, and let's just stick to the equal sense so that I don't have to worry about polynomials. So there is a map in the other direction. And then, I mean, it's kind of, morally it goes to this module, but the fact that it lands there is non-trivial. And what you do is you pick two elements, A and B. So this is like I's and Wi's. And you map it to a function on the torus, which is defined by a sum over column. So you take new all integer points intersected with the column A times the positive outcome. You put x1 to the power mu1, xb to the power mu d, and then you put some product of linear forms in the denominator, and you use kind of the dual basis to w's. So, I mean, there's some kind of possibly better choice of whether to dualize or not, but it is what it is. And then you have to multiply it by inverse determinant of B and sine of determinant of A. So that everything respects the symmetries in the Steinberg model. So this map you can easily write down. I mean, it gives you some collection of functions. Now the question is, are these all polylogarithms? And that requires something that Federico was doing when you restrict to rules of unity, but now doing it on the level of functions. And so there's like several non-trivial things going on, and it turns out that so if you ignore things here, so this is kind of well defined, except so the partial fraction identities guarantee you that whatever the changes you do in B are respected, because you just changed the summation function. But when you change the cone to one of these opposite cones, so if you take summation here and you replace it by summation here, it corresponds to some non-trivial identity of these functions, which luckily is true. But it is only true modulo kind of logarithms of characters corresponding to this direction. And it, it's done. So you get some kind of analogs of the inverse relation for the multiple polylogarithms, but kind of much more general thing. Okay, and so, but so there is some work to prove this is well defined, and then there is work of proving that whatever thing you happen to have here is successful in terms of multiple polylogarithms. It actually lands in this space. And that turns out to be some elementary kind of geometric theorem, which is what I want to talk about in the rest of the remaining 5 minutes. So there's also a way from this abstract theorem to prove the original statement that I started with, that everything is generated by one type of polylogarithms. But it's like it requires a little bit more, but it's almost an exercise if you have that map. So what I want to talk about is how to reduce a general sum like this to multiple polylogarithms by drawing some pictures. So the key point is, and I'll do it for d equals 3, because that's the only case in which I can draw pictures at all. But so the point is, polylogarithms correspond to pairs of variables. So it's not arbitrary, because here we have some relation between the vectors appearing. And it turns out that, well, maybe I should use both. It corresponds to pictures like that. So I'll have a one white and one blue triangle. One corresponds to one Steinberg, the other to the other Steinberg. So this kind of is an element in Steinberg tensor Steinberg. So yeah, maybe I'll use P1, P2, P3, and Q1, Q2, P3. And the property is that P1, P2, P3 is whatever it is, but then the Q simplex has the first vertex is the same as the P simplex, but the other ones are lying on the consecutive edges of the P simplex. So in this case, it's just anything that's combinatorially equivalent to this picture. So Q1 coincides with P1, Q2 lies on the line P1, P2, and Q3 lies on the line through P2 and P3. So these are polylogs. On the other hand, we have pictures which are kind of generic. And these are elements here. And now we want to apply relations in the Steinberg module to get from a generic picture to something like this. And it turns out that you can do it basically by just drawing some subdivisions. So first of all, I'll try to present the proof without writing anything except drawing pictures. So first of all, if you apply relations in the Steinberg module, you can always get from a triangle. So this is some P1, maybe S1 plus P3. You can rewrite it as a combination of triangles with 2 points on this line. And basically, you draw a picture like this, and then you kind of add this thing, and then subtract. So basically, you take the three triangles formed by 2 points on the line and 1 point in the triangle, and then you can write any triangle as a combination of these more special ones. So you kind of reduce to a picture where you have a line L here, and you have one triangle which is the P triangle, and the other triangle is the and now what we want to do is
P1 has to equal P1.
No, but I'm kind of starting here.
You're not taking the triangles.
Yeah, I want to end up with this with a combination of these pictures.
So you're taking an intermediate situation.
Yes, it's intermediate situation. So I start with a generic thing. I apply operations like this to both the green and the blue one, the white one, and I end up with a situation where the position of the sequences is like that. And now I kind of have to subdivide one or the other. So I pick a line through these 2 points, and they end up here, and they either separate, split the P triangle or the Q triangle into 2. So I get 2 similar pictures. I'll just worry about one of them. And it looks like this. And now I kind of add this thing and subtract it. So I get so plus and minus. So I get 2 pictures which are the way I want them. Using these. So in each stage you actually get a bunch of triangles, but I only keep track of the type that appears. And yeah, it's exactly the same type of picture, but one of them looks more defined. But they're exactly the type that I want. So you just apply a bunch of Steinberg relations, and you get from a generic one to a situation like this, and that's your proof essentially, because now each picture like that can be recognized as a multiple polylogarithm.
But it also tells you how.
it is completely explicit. So, and actually, it tells you that in the process of doing that, you have to introduce higher and higher roots of monomials, because every time I make an intersection of two lines, I have to solve a linear system. And you can kind of keep track of that, but it becomes a mess. And that's why you couldn't find anything in depth 3, because if you do this operation, you kind of have to go to very high roots of monomials to find anything interesting. And it's kind of hard to see it without this combinatorial description. And so what's nice, so this is kind of the part just about proving that this is well defined and it lands where it should land. But you can also, so this, the way I did it, you can actually fix this line in advance, and you arrive at only special configurations where this line is fixed. So in fact, it tells you that not only you can reduce to special polylogs of certain type, but you can actually impose some condition on the arguments that appear. And you use this type of reduction to prove the result about T111n. So you basically, you can choose this reduction in such a way that all of the polylogarithms that appear are just one type after you do some elimination. So that's roughly the idea, and I think I should stop.
Thank you very much. Any questions?
So ultimately, then the proof you're saying has a manifestation in terms of these pictures.
Yes, yes. Yeah.
It says some statement about the equivalent class of pictures.
It's a statement about the Steinberg tensor Steinberg and like some choice of basis in that. Of course, you can take two bases, like one for each Steinberg, and then take a tensor product. But this somehow is more interesting, and this is the one that's more useful for the Hopf algebra structure. So yeah, but it's a little bit.
Can you say something about that exercise to show that all polylogs are reduced to one?
Yeah, I mean, this was, I was kind of trying to explain. So what you do is you basically write a combination like this, times some coefficients that you pick. Product. So you pick some vector, auxiliary vector alpha 1, alpha d into b, and you consider this sum over all n1 plus nb equals n. And so what you do is, if you apply this, the Steinberg map, it sends you to something very simple. So it's basically just the combinatorics is the same. And then the polynomials, when you collect everything together, you get basically a power of one linear form. Something like that. And now the point is, you can apply, so there's this whole story about there are two types of, there's a dual type of relations for Steinberg module, which I didn't talk about, but basically you do it by dualizing the projective picture. So now instead of adding one more point, you can add one more line. And the point is, so you have this statement with fixed line, and you can have also a version of this statement where you fix the point P to be something predetermined. And if you apply this dual statement and you pick this point to be exactly this combination, so you pick P equals Q equals this line, then if you look at the, so you get a reduction of this element to a collection of polylogs where P and Q are like that. But the point is that the polynomial tells you what are the weights appearing in the expression. So if you now consider expand it in terms of polylogarism, it only involves D111n. So, and that's the end of it. Then you have to apply it to a bunch of vectors and eliminate all of the, so this is like a finite combination that you could express, and now you have to do it in many different ways. And that's why kind of any individual function expression is so terrible. So we couldn't even find one explicitly. Because you have to do some Vandermonde type inversion a lot of times.
Any other questions? not, then let's thank Daniil again.